thinking the same.
Okay.
All right, so number 57, I'm going to write here. Oh, and I haven't shared my screen yet. So let me share my phone here so you can see kind of my doodle pad. Yeah, good. All right. So number 57, as you said, has this phrase in it about low frequencies and high frequencies. And let me begin. Well, I should give it by probably reading it for anybody who might be just like tuning in here. So it just said, all right. So 57 says, in the figure. So let me show the figure here. They've got an AC source kind of in the middle of it. And they've got two branches. The first branch is a resistor with a capacitor. They list the resistor as 200 ohms, the capacitor 200 microfarads. The other branch also has a resistor, 100 ohms, and an inductor. And what I want to kind of point out before I get started is we've dealt with already capacitors and inductors, but with DC circuits, okay? And so this whole chapter is about, okay, now let's make our power source change. And I think you got the gist of that. But let me go back to capacitors. If we just had something that looked like this, where I had a DC power supply, I'll just say 20 volts, and maybe I had one branch that had a capacitor and a resistor, and maybe just for the fun of it, another branch that just has a resistor, why not? And I said, what would happen? And I said, the instant you turned it on. Okay, so maybe I should put a switch here. And maybe you remember some of these homework problems. Maybe you remember it was part of the exam where it said, okay, what would happen right when you close the switch? And our thinking went along this line, that the capacitor right here, maybe, and all right, capacitor is charge divided by its voltage. Okay. Or its voltage would be, maybe this is a better way, it's charge divided by its capacitance. When you first close the switch, you would say, well, you haven't had time for any charge to build up. So there's not any voltage on it. And if there's not any voltage, you can just kind of ignore it and treat it as like it was just a wire, because a wire, we would say, has no voltage. Okay. And then we would also say, after a long period of time, what would happen is you would build up so much charge that the charge would come to the point of creating enough voltage to stop the current. I guess I don't really need this branch to have that discussion. And so there were two answers, because one was with basically no charge on the capacitor, and the other one was with a fully charged, enough charge that it blocks. Now, maybe I'll pause and ask you, are you good with that?
Yes.
Okay, so I'm going to play the same game to this problem.
Okay.
So this problem, what we have is an AC source. And well, so what that means is current flows first in one direction for a moment in time, half the cycle. And then the current flows the other direction. And what that would mean, I think my, it froze, I don't know why. I was trying to quickly set up. Each Friday I have to turn off my screen lock. And once it locks, it just kind of freezes there. So let's see if that comes back. Okay, so let's turn off the timer there. It's funny, I always forget to turn it on when I start on Friday, and I always have that first problem. And then at the end of Friday, I always forget to turn it off. And I usually wake up like in the middle of the night, Friday night, early Saturday morning, and my phone light's still on. I was like,
Oh my
oh,
God.
it's recorded, and the screen's still going. Never shut off. All right. Okay, so what I was trying to say here is that where this AC source is, it's essentially charging the capacitor and then discharging, charging it and discharging it. Okay, so if you do this at a fast rate, you don't give the capacitor enough time to build up any charge. So this is like when you first close the switch. Without any charge, you can just think of it as a wire.
Okay.
And so I'm going to say that for high frequencies, so maybe I'll put it right here. If omega is big, without really getting into how big is big, but when it is really big, you can say that the capacitor is just a wire. It's like it's not even there.
Okay.
That statement is the same as what we were doing earlier on when we say we just closed the switch. That's what I wanted to connect it to. I wanted to connect it to what we did. I think we did this in chapter 28. So connecting this chapter back to 28, that's going to be my logic. And the same is true if omega is small.
Okay.
If it's small, then the current flows in here and fills up this capacitor. Now, I know when I say fill it up, it really depends on how big the capacitance is. Okay, but just talking general principles. If we are at a low enough frequency, we could actually build up enough charge here that this is stopping all the currents. And so there is no current. And so that's the same discussion that we again had in chapter 28 when we said, well, what would happen after the switch is closed for a long period? So I'm going to use that. Now, before I go any further, I might also say this. We have a mathematical equation that's called the reactance. And the reactance was a mathematical way of saying, how much opposition does that capacitor present to stopping the current? We don't want to call it resistance, but just for the moment, why don't I have you think about it as resistance? So it's again, not the same as resistance, so we don't want to call it resistance, but it has the net effect of opposing the current. And so I like to use the word oppose the current. It doesn't resist it, it opposes it. And so your author and I, right now I'll just give you the formula, went through and said, this was the equation for the amount of opposition. So you can see that if you have a big or a high frequency, you get 1 over big, which 1 over big equals small. So I would, again, say you can look at the math and say, if you have a high frequency, you have very little opposition from that capacitor.
Okay.
But if you have a small frequency, then you would have 1 over small, and 1 over small equals big. And so then you have a big opposition. Now, I'll talk about the inductor, but I want to do the capacitor first since we've been doing that one a little longer and I thought you'd feel more comfortable with it. So let me jump over here to the question. It says, if the RMS current delivered by this 45 volt RMS power supply when A, the frequency is very large, and B, when it is very small. So as far as the top loop goes, I'm going to say this. For A, when the frequency is very, I'm just going to ignore that capacitor.
Okay.
I'm just going to say it's a short circuit. In fact, when I'm going to say when you take, but that's presumption of us, me, because you might be in the circuits class. Most are not. Are you in the? You're not in the circuits class.
No, I'm not.
Okay. So, when you or if you go into the circuits class, there's a phrase we like to use in circuits classes that we say, treat capacitors as an AC short circuit.
Okay.
And here's what we mean by that. We say, okay, if you have an AC source, and so for A, I have a resistor up at the top. That's the 200 ohms. And nothing else. And so that's how I'm going to do at least the top branch of A. I'm going to say there's not even a capacitor there because I'm at a high frequency. And a high frequency, as we said, means that the reactance is small. That means you can just ignore it. It's, maybe only 1 or 2 ohms compared to the resistor. It's negligible. So I'm just going to ignore it. And in part B, where they say we're at a small frequency, I'm going to do this. This would be like having a resistor and then an open switch. Because there is so much opposition. When I talk about, the frequency being small and then this being big, this reactance here could be like millions of ohms.
Okay.
Which is why I could just really kind of ignore the resistor. The resistor is only 200. And if this is like 2 million, basically no current's going to go through. So that's the idea of this is more of a, instead of doing a numbers game and actually do a calculation, they're saying, just kind of understand the general physics, the concept. And so the concept is for high frequencies, a capacitor is a short circuit. Mm-hmm. For low frequencies, it's an open circuit. Okay. Now, I'm going to come back to this drawing. Let me call it page 1. But let me also, then here on page 2, let's talk about the inductor now. The inductor is a little newer to us. The inductor is a result of Faraday's law. So that was 2 chapters ago. So hopefully you're getting a little more comfortable with Faraday's law. I'll put Faraday's law here, which I guess is chapter 31. And it says that the EMF, which I will call it the back EMF, is the how the flux changes. But even though this was chapter 31, when we applied this to a circuit, we kind of separated out that the flux was changing because the current in the circuit was changing. Okay, but here's the important thing I want to get at. Notice then, in a statement like this, you would be saying something to the effect that if the current is changing very quickly, so high frequency. Mm-hmm. So if omega is big, then the back EMF is big. Or if we put it in mathematical form, we learned that there was a reactance for our inductors as an omega L, and that would be big. So what we're saying is really the reverse of what we just said for the capacitor. See, the capacitor, we said for big frequencies, you would have a small reactance. The inductor is the reverse effect, where big frequencies is a big reactance, and therefore is stopping the current. So if I come back here to my drawing on page 1, and say, all right, down below, how would I draw the branch with the inductor? And for high frequency, I would treat it as an open circuit.
Okay.
And for low frequencies, I would treat it as just a wire. And this is a little newer to you, but if I could do the same kind of description that I did here, which I guess is chapter 28, when we did our DC circuits in this last chapter, 32, I don't, at this point, you might not be feeling completely comfortable with chapter 32. You just learned it, last week when you were first introduced to it. But if I would do this, if I would put, a 20 volt power supply and a switch, and this time let's see, last time I guess I put a capacitor and a resistor. But if I were to put an inductor and a resistor, and I ask this question, what would the current be the moment I close the switch? Well, I would say the moment I close the switch, the current is changing so quickly. It's trying to go from 0 up to something.
Mm-hmm.
That the back EMF would be equal to 20 volts. And so maybe I'll in my diagram say this is pushing back with 20 volts, and there'd be no current.
Okay.
So right when you close the switch, I would say the back EMF or the reactance is so big, you don't get any current.
Okay.
And that's what I'm trying to say would be the equivalent in this chapter 33, where you have a high frequency. If you have a high frequency, you are constantly trying to change the current back and forth at such a fast rate that this inductor is saying no current. No, it's constantly saying no current, no current, no current. And it's like a switch has been opened here and not letting any current go through.
Okay.
And that's what I mean by it's the opposite. But on a reverse effect, we went back to chapter 32, and I said, what if I closed the switch and it was closed for a long period of time? Well, for something like that, I would just ignore the inductor. I would say the inductor has become a wire.
Mm-hmm.
I would say something like that. The DI/dt has settled out to be 0. And it's just like a wire. And so the current would just be Ohm's law, where I take the 20 volts and I divide it by the resistance. I don't even have anything. So, by the way, a little side note here, maybe your reward for coming to the office hours here today, but notice that on the last test, you had a question related to capacitors and current when the switch was first closed and first opened.
Mm-hmm.
Be ready for that on the third test where the switch is opened or closed.
Okay.
It's just, maybe it's so obvious to students, I don't know, but it's just like, well, hey, we did it for the capacitors on the second test. Why wouldn't it be there for inductors on the third test?
And so when the switches are open and closed, then we're really just looking at the resistance. Is that wrong?
Well, a better word is the reactance.
Okay.
Again, I'm trying to say that the reason a inductor or a capacitor opposes current is because inside of them is a built-up electric field.
Okay.
For the capacitor, the built-up electric field comes from the actual charges on the capacitor.
Mm-hmm.
For the inductor, it's a bit more complicated. In fact, it kind of goes back to James' question that he wants to ask: is the inductor makes its own electric field on itself which comes from the changing magnetic field, but the magnetic field also comes from itself because of the current. And so the current makes a
Okay.
field, but it's changing, and then the magnetic field makes an electric field. So I'll hold off on that for a little bit when I get to James's question. But for your question, I will just say that you are getting a back EMF, you're getting an electric field. And so it's better to say there's a reactance, not a resistance.
Okay.
It's kind of like back in physics 121 that if something couldn't move, let's say, so you try to push something and you say, oh, it's not moving.
Mhm.
Well, why isn't it? Or it's hard to move. Why is it hard to move? Well, one option is it's hard to move because there's friction. Well, that would be like resistance. But another reason it might be hard to move is because somebody's on the other side of that big box pushing back. And so there's a force. So I wouldn't say it's hard to move because of friction. I would say it's hard to move because of another force. And so either way, the box is hard to move. And that's kind of what we have here for current. The current can be hard to move because of resistance, that's friction, but it can also be hard to move because there's an electric field pushing back, and that's reactance.
Okay.
Now, just to throw another word out there, the totality of the two of those together is called impedance. So if you just kind of want to be all encompassing, you say, well, how come the current's not flowing? You would just say, oh, it's the impedance.
The impedance.
Because the impedance is a way of putting together both the resistance and the reactance.
Okay.
And in a complicated circuit, you have both of them.
Okay. Thank you.
Those are the subtleties on the word. But finally, maybe I hope I didn't talk too long here, but finally, maybe I'll get to your question here, because now this is how I'm going to deal with the circuit. So when it says here, find the RMS current delivered, I'm going to say, okay, across the top branch, the current would be the RMS voltage divided only by the 200 ohms.
Okay.
Because I'm basically saying the capacitor part of it is out of the picture. So that would be 45 divided by 200. Now the bottom part, because of this open here, and I probably don't even need to do a formula, I'll just say it is voltage divided by something really, really big, which means zero current. And so the total current is the sum of the two, but nothing's in the bottom of it. So grabbing my calculator, I would go 45 divided by 200 and get 0.225 amps. Or, let me just check. Did they say RMS? Find the RMS current delivered by the 45 RMS power supply. Yeah. Now, for B, kind of the same logic. In the top one, I would do this. I would say it is the voltage divided by big. Because again, the capacitor blocks it by a lot when you're at a low frequency. And the bottom one, it's like the inductor's not even there for a low frequency or for a switch that's been left on for a long period of time.
Okay.
So this would be the 45 divided by, and I didn't put it in my diagram, but that was a 100 in the bottom piece. So 45 divided by 100 would be 0.45.
Thank you.
And I better check my answer since it is so easy to make a mistake. Good. I didn't this time. That always feels good when you don't make a mistake.
Yes, always.
I'm sure you can relate. But at the same time, it's also one of the biggest learning processes. I have found that sometimes I make a mistake so badly. It's like, okay, I don't think I will ever do that again. That was just So anyway, hope that all helped. I hope.
For that explanation, and sorry for making you wait so long, James.
Oh.
No, that's okay. I don't mind. Sorry.
All right. Hey, James. Now, you're. Let me go ahead. Since you came in here, I want to answer your question, and I want to just kind of get it done with this one, even though like I said, I was in a long meeting before this, so I do really need a break. So
Why don't we? I can wait. I got plenty of other windows pulled up with other physics stuff to where I really don't mind. Seriously.
No. I'm energized right now. So okay.
You're
so,
okay. You're hyped up.
I'm okay with this. Well, I'll tell you what. Let me do let me throw it out there and then let you think about it on the break, and then you might want to do a follow-up question. How about that?
Okay, yeah, I'll give you some because this is maybe a little bit out of left field, not that far.
No, and it really ties together really well with Ariel's question, because you asked this, or I think you made a statement. You said, according to Faraday's law. So let me write down Faraday's law. A change in flux produces an EMF. And I don't disagree with that at all. That's why in my response to you, I said, well, I would use different words. So notice I didn't say you were wrong. I just said I would do words a little different, because it sounded like you were trying to go to the fundamental physics on this to get an understanding. So I'm gonna do this step and say, let's just say that this N is really because you took a wire and you wrapped it around a bunch of times. Okay. So if you were then to have this magnetic flux, and so I'll do the green arrows for the magnetic flux, go through this coil, then you would want the N. In fact, I would even go one step further. This was kind of your question, is I would probably want to know, for a problem like this, what the current is. So I probably would take the EMF and divide it by the resistance in that wire, which means I would have something like minus N over R for the resistance in that wire, and then I would have the derivative of the flux. Okay? Now, again, there's nothing wrong here. And you might even use this phrase. You might say something like, oh, the change in flux produces a current. And okay, but that's not the fundamental physics. Do you see how the current is kind of a secondary effect? The current is really the result of the EMF.
I do see that.
Because I'm going to do one step better with you. I'm going to say that the EMF is actually the secondary effect. The current is the third effect. And that's what I really wanted to show you. And that's why I would say I would use different words. Because watch this. If I did something such as this, what if I just said there is a magnetic field and it's changing, but there is no wire wrapped around? So if I said there was no wire, I think you would be if there was no wire, I think you would quickly understand that there would be no current. Fair enough?
Fair enough.
Okay, you're like, oh well, yeah, of course. There's no electrons in that wire to be pushed. So the current is not the fundamental effect. All right. Now, I guess I would also say then you would not have N turns. There's nothing to talk about a bunch of turns if you don't have the wire there. Or maybe more fundamentally, you might say, if you drop the N, you're talking about one loop. And if there's not a wire, I guess it would have to be kind of a mathematical loop. And that's exactly what I want to put together here. So let me write Faraday's law this way. Let me drop the N. let me replace the symbol for flux with the integral that the flux represents, B dot dA. Now, let me go back to chapter 27 on the definition of voltage. Voltage was this minus E dot ds. And let me put that into here and see what we get. It's just kind of fun to see. And it really adds to the physics. If I put E dot ds, so what this means is the electric field on some path, some mathematical path. Maybe now that helps you why I'm going to say here. Let's take wire to the wire. Let's do a mathematical path. Because the mathematical path could have an electric field. But I'm not sure I would say it has a current if I don't have a wire there. But I could still have an electric field. And that's what I'm trying to point out. I'm trying to point out here that if you take away the wire, do you still have anything? And I'm going to say yes. I'm going to say you have, in the shape of a loop, an electric field. But there's no point in calling it, hey, we got a young learner over there. All right. All right. So start that science early. I'll be good for you.
Yeah.
All right. So, but James, I'm going to say here, this loop right here is really going to, if I can convince you here, be an electric field. And that electric field would exist even if you took away the wire. And we would only really be talking about a voltage and a current if we had a wire. But if you really want to understand the physics of it, which is what I got out of your problem, is I would say, let's get rid of the wire for a second and see what we get. And this is how I'm going to do that. So I'm going to just do one mathematical loop and say, watch, this will actually show that the changing magnetic field produces an electric field. And that's the words I would choose to use with you. You said back in your email that the changing flux produces a voltage, and that's true. But what I want to convince you is that's really a secondary effect. The primary effect is coming when I'm going to say a changing magnetic field produces an electric. And this is the electric field that gives the back EMF on that inductor that I was trying to help Ariel with a moment ago. It's the changing magnetic field in the inductor because of the current that results in a back EMF. The back EMF comes from an electric field. So it's an electric field that's pushing back on it. Now, here's the math part that you said you might like. If I apply Stoke's theorem says that you could change a path integral into an area integral when you do the curl. Now, I need a pause right there because that can get above our class level right away because that's math.
I'm at least I'm at least medium. I got
So have you had math 200?
yeah, and you mentioned it, so I've been going pretty hard. I got
Okay.
I got
good for
Stokes
you.
right here.
Okay.
I
Okay.
have yeah.
Okay. But then now, this is the purpose of Stokes' theorem, is because now since you have an integral over the same area, you can get rid of the integral. Or put another way, you can differentiate them away. Before you couldn't do that because one was a line integral and the other was an area integral. But now you can. And so now you have the curl of the electric equals to the derivative of the magnetic field. And I guess to be a little more accurate with my mathematics, since this derivative is outside of the integral, I should write this as a partial. So in this case, it doesn't really matter, but I don't want us to get, bogged down in the math.
I want the math police to come.
Yeah, math police. That's a good one. All right. So now the curl, and here's where maybe I'll take our break. But the curl in itself is pretty complicated because it would have this matrix like the I hat, J hat, K hat. Then you have the gradient. And the gradient is derivatives with respect to space. And then you have the components of the electric field. So that would be a determinate way of writing out the curl. And then, of course, these would have three components. So you would have the derivative of the magnetic field, the x components, I hat, plus the derivative of the y components, plus the derivative of the z component. So mathematically, this can get pretty messy.
Honestly, how you've got that written there isn't too bad, you know.
Good. And actually, that's a good sign that you're getting used to this because when you,
it is a lot.
when you try to expand out that determinant, you put I hats with I hats and J hats with J hats and K hats with K hats. And this can get pretty messy. But if we kind of limited our discussion to say, coming back to our picture and just say, let's limit it that we have a magnetic field that is only in the X direction, then we could say that this term is 0 and this term is 0. And that really simplifies the other side. And if we only did the X component, then we would have something that would look like this. We would have the partial of the Z component with respect to Y minus the partial of the Y component with respect to Z, then equals to how does the X component change with time? and that in itself is a pretty nasty equation, but let me pause and just put this in words. Here's the words that I would have used to describe. I would say a changing magnetic field then produces an electric field.
If I imagine my magnetic field kind of along the x-axis.
Yeah, like this.
Okay, yeah, and then I guess that's the rotation would be in the y, the YZ plane.
Right, so you would only have Y and Z components of your electric field. That's exactly what this is saying.
So that's my change vertically, and that's my change horizontally along the Y.
Well, good. So you're seeing something important here. You're seeing a couple of phrases I would put. I would put a changing magnetic field produces an electric field. That would be my first phrase. My second phrase would be the direction of the electric field is in a plane that is perpendicular to the magnetic field.
I see that.
Now, it also has to change, and I didn't prove this. I didn't do enough math to prove it would be in the shape of a circle. But if you have only changing in the X direction, what you would have is this circular effect, which is why if you make a wire, the electric field pushes through that wire and makes a good inducting effect if you coil it up. That's why our inductors and coils are the ones we choose to use because they're in a direct direction of the field. Or maybe I shouldn't use direct direction. They're in the direction of the electric field, which is kind of this coil effect. Okay. Now, part of the reason why I couldn't continue on to solve this mathematics is because there's not enough information to complete this equation as written. And in the next chapter, chapter 34, you're going to see this. You already saw half of the equation. We called it Ampere's law. We said the integral of the magnetic field around a loop is equal to mu naught times the current inside of that loop. But what the author and myself are going to introduce you to is that was a good first step, but Maxwell shows that that cannot be the full story. There's more to it. And it turns out that there needs to be another term that relates to the electrical flux and like I said, this might be a good place to kind of stop with the math and let you think it through. But if you do the same thing with the electrical flux and you do a Stokes theorem, you will get something on this side of the equation, which is how the electric field changes with time. And over here, you'll get something like the curl of the magnetic field. And if you put then this equation with that equation, you can begin to solve and realize that there is some unique patterns, certain things that can exist and certain things that can't exist. And that was, Maxwell's brilliance. And then you could show that this has to be a circle.
Okay, well, we'll definitely have to do that. I finished chapter 34 and I found a YouTube video that works out it derives the differential forms of the equations from the integral forms.
Oh, okay.
So I don't really understand it yet, but I've seen it, I'm just cracking the surface. But going back really quick to Faraday's law, I don't, how can I understand Lenz's law? I mean, maybe from like the differential form, because it seems like we have an induced current, and then that gives us a magnetic flux, which we have a current, a primary current, and that, as it's increasing, creates a magnetic flux, which induces another magnetic field, right? And a secondary. Am I thinking that right? I'm trying to think of Lenz's law.
Okay. All right. Wait. Okay. So let me backstep. You said if you wanted to think about it in terms of the differential form, I would say this. The current made a magnetic field right here.
Okay. Yeah.
And since the current is changing, I would say the magnetic field is changing.
Maybe it's getting stronger as I'm ramping up. Okay.
And then I would say, since the magnetic field is changing, that's going to create an electric field. Then I would say that electric field would make an EMF. That EMF would then make a current. That current makes a secondary magnetic field. And that direction of it is such that it opposes. So I think there's quite a few steps before you get to the answer of the secondary magnetic field.
So if I were to sum up the rate of change of the flux, the magnetic flux through this surface, accounting for the initial one and then the secondary one, is it zero? Do they cancel out perfectly so that the net change is never anything,
No. It only does it at the first moment. So you only get a voltage I'll write it in a circuit.
Okay, I think I got it. It's because it's the change of the magnetic flux that's
Yes.
created. It's not the, so I could have like a billion Teslas going through
Yes.
there and nothing coming back.
Well put. Sorry, I didn't notice that. Yeah, it's all about the change. It's not about
No, I
how
didn't
much-
articulate that. That's subtle, you know. That's
Yeah,
something
yes.
that's hard to wrap your noggin around. Okay, awesome. Thank you, Dr. Young.
All right. Hey, we'll take a break and give that a thought for the next 37 minutes, and we'll come back if you have more. I know there'll be some quite a few questions from chapter 33.
Go ahead.
My name's.
She wants to say hi to you.
My name
Hi.
is Lee, and I like your background.
Thank you. I wish I was there.
Yeah, me too. Okay. Thank you, Dr. Young.
Thank you. Bye. I watch your videos with my mom sometimes too.
Oh, good, good. You're gonna be a little scientist someday. I like it.
Yep, hopefully. Thank you, Dr. Young. I appreciate it.
All right. Take care.
You too.
Oh, Chen. Oh, great. You've got some questions from me. I'm gonna write those down so we can get them on the break here. Let's see. We come back in 25 minutes or 26 minutes, 36 minutes. So number 12, number 19, number 21, 24, number 27. Ooh, gonna keep you busy in a fun way though. All right, 42, 45. I was telling James how this is much more enjoyable than my last meeting I was in. 45, 47, 50, 57, and 68. Nice. All right. Take care.